has written the thesis that I use as the back of the book check on my results in my research. So he's been at LSE as a master's student, a graduate student. Now he's there as a postdoc, and he's going to be here out parameter estimation and nowcasting. No, nowcasting in scenarios. So welcome.
Thank you. If some of you have listened to my previous talk, I apologize for the perspective. But so today we're still going to talk about the nowcasting algorithm descent. So this is the first. I would like to thank to my supervisor Lenny Smith for the guide to supervise me for all these works. Mainly, I will discuss the method that works in the perfect model scenario and imperfect model scenario. Also compare the state of techniques like 4D bar or the sequential method like ensemble common future. I think maybe John T have the idea, or it does kicking ass for the compared with the other method.
I'm a convert. I really am.
So just for the perfect model scenarios, the experiment is designed for finite dimensional nonlinear deterministic dynamic systems. We assume the observations are generated by perturbing the shoes with IID noise, and we assume the function of the system are null, and also the noise model distributions. So our goal is just to find an ensemble to construct an ensemble of initial conditions at t equals 0, using all the information in the past. So right now it is very common to use the ensemble techniques to maintain or to account the uncertainty in the forecast and in the nowcast. So there are a variety of ensemble techniques, but most of them fall into these two categories. One is we generate those ensembles directly, like those is sequential method, and one is generate an ensemble like perturbations from analysis from a control trajectory. For example, using the 4D bar, then do some HVD on it. So our method falls into the second category. And this whole method is all the method. The theoretical background of this method was first introduced in Jordan Smith's 2001 paper. If you're interested, you can have a look. Here we just give a brief introduction of the method. So we define a sequential space, which is given n observations, and which each observation are in the n-dimensional space. So we define this sequential space that contains any series of model state space. Then we define a mismatch error cost function, which is basically the function forward image minus the state in the sequence space. For example, here the mu, we define the mu to be one of the series of the model states in the sequential space. So usually these series of model series, they are not on the trajectory; they are pseudo-orbit. That will give us non-zero mismatch error cost functions. For example, particularly the observations. So our method is very simple. It's just minimize this cost function using some minimization algorithm. For example, the gradient descent, and we minimize them starting using the observations. For example, we have now here we have considered these 6 as observations. We initialize the minimization, the mu 0 at the iteration. At the minimization, when the minimization started, we use the observations to put into the minimization algorithm. And at the start, all these red arrows are corresponding to the mismatch error cost functions. So the sum of all these red arrows will be the mismatch cost function. Or what we are targeting to minimize these errors in the sequential space. And when we iterate the gradient descent, we can see these red arrows, all of them getting smaller. So the cost function getting smaller, and smaller again, and eventually it converges to a trajectory manifold. So there's a nice property of these cost functions. It has no local minimum other than 0, so that you will always converge. You will always finding a trajectory manifold in the end. So all the local minimum defines the trajectory manifold.
Actually, I should just say that this, obviously based on my own experience of yesterday, that although it's minimized if and only if you lie on a trajectory, that's totally clear, even for non-differentiable properties. For numerical reasons, it can bottom out before it actually reaches the trajectory.
Yeah.
For numerical reasons, sometimes the minimizer will bottom out before it actually reaches the manifold.
Oh, yeah, that sometimes that maybe is because when you do run the gradient descent, you set up the step too large so that it misses up the bottom. You can set up your steps smaller so that it will converge to the.
So it's like also the neutral nodes, and so
yeah.
Just like everything, you get to a place where the gradient is so small that numerically.
Yeah. Now I've set the relative tolerance to 0, right? And I'm minimizing on the basis of the absolute tolerance. And it's still bottoming out before it minimizes absolute tolerance. But I think it's purely numerical.
Yes.
Neutral.
So a lot of people think this method looks pretty similar to 40-bar, but actually they are very different. So they're different in many ways. So firstly, will be they're different in the cost functions. So this is a 40-bar cost functions. What 40-bar does is minimize the initial state. Here will be the y and minus n plus 1. So that any of the initial condition here, it defines all the sequence of y here. So basically yt plus 1 is fyt. So in that case, these cost functions only depend on this initial condition at the time when it started. So it's minimized in the state space, only in the state space. Well, for our method, we know that we don't minimize the cost function in the whole sequential state space. That's very different. Oops. I think this might be some setting was not consistent with the Apple laptop. So for the second, the error should be gone here. The second thing is the noise model assumptions. So for 40-bar cost function, it's basically generated from the observational noise model. You have to assume some observational model, then you derive the 40-bar cost functions. Well, for gradient descent cost function, it does not depend on the noise model.
In fact, the observation error doesn't come into the method at all.
That's right.
Sorry?
The observation error doesn't enter into the problem.
It doesn't enter into the minimization algorithm at all. It's the noise model isn't. The observation only used to start with the minimizations.
But it enters later.
It enters later. And also for the assimilation windows, for 40-bar we all know that it has problems with when applying the longer window length. While our method doesn't have that problem at all, which makes it so. We always want to use longer windows because we want to use more information in the observation than dynamics. So 40-bar you will find either it's difficult to locate the global minimum when you use longer windows, or you have to compensate that using shorter windows, which you will probably lose the information in the observation and the dynamics. Then to form an ensemble, so now we use the gradient descent, we can get a control trajectory or reference trajectory. To form an ensembles, what we do is to see here is the observations, and which is generated by truths. We don't know that, and we first generate the reference trajectory by using the gradient descent result. Then, based on these reference trajectories, we try to form. We need to form an ensemble of initial conditions. To do that, we first generate a bunch of candidate trajectories, which is we choose. We often use either sample the local space or perturbing the observations and run the gradient descent again. Should be something down there. Like Jonty said, we actually have some numerical issues with the gradient descent, because although it's theoretically converge to the trajectory, but you can only run your computer with finite time. So it will only give you the pseudo orbits in the end if you only run your computer finite times. So what we use to generate the reference trajectory, we often use the middle components of that pseudo orbit and iterate forward. Use that to define the reference trajectories. And we, for some point in the local space, we just perturb in the middle point of that reference trajectory and iterate forward, generate the candidate trajectories.
So by middle, do you mean the middle of the interval over which you've done this?
Yes.
So you're working with a system here where you can take any point in the trajectory and you can generate into the past or into the future. Since you're only interested in the nowcast, you only look in the future. Okay. But by taking the point in the middle.
Sorry, what did you mean by the point in the middle?
So say we have a reference.
Just point at it. Identify it on the screen.
So if this is the reference trajectory, we take in things we given like numerical constraints. So those reference trajectory is not really a trajectory; it's a pseudo orbit. They are not lying on Q. What we take is take the middle point for take this point here, and using the model dynamics to iterate forward to generate the trajectory.
I think it's a subtle and interesting point, because if you're doing an old-fashioned variation-based summation, I mean, you're at the end, I'm at the beginning, but it doesn't really make any difference. But the thing is that it's quite possible that this method has a tail that wags slightly more. You know what I mean? Than
yes.
In the middle.
Yes.
Yes.
Yeah?
Yes.
And I don't think that's something that I fully appreciated.
Yes. I think that for those middle points, because they're taking information from the past and the future,
yeah.
They have more. They are more quality than the end points.
Yeah.
But I mean, to some extent, the discussion of the middle point is a bit of a red herring, because the next slide, right? You get for an in-point pseudo-orbit, you get that defines in trajectories, assuming things are invertible.
Mm-hmm. Yes.
And then you can use the observations again and just see what their relative, how well each one compares to the observations. So you can generate many candidate trajectories, one for every point on the pseudo-orbit, right? And then the issue is that you then use the observations again. You can then use the observations again to see what the quality of those orbits are if you go backwards in time.
So given
so
those,
this choosing the middle, this midpoint trajectory, is that because you haven't converged? If you would really have convergence,
it's not exactly equal to zero.
So even if the algorithm has converged, you're not looking for a point. So data assimilation with uncertainty doesn't make sense to really look for a point, right? The idea is to try to get a PDF, but we can't, so we want to sample. So the fact that like everybody else, right? You generally think that the guy in the middle, in a variational thing, you think the guy in the middle tends to be closer to truth, and we do that. But there's no real need. If that wasn't the case, it's really easy to generate the trajectories from the other points on the pseudo orbit, right? At least the first half, because you don't have to go backwards in time, and then you can just look, right? You can just see if they happen to be saying they go flying off far from the rest of the observations. They're just very poor candidates. Does that make sense? I mean, if we had to start somewhere, we'd start in the middle, and we do. But we don't. We actually want to get all those gray lines, and checking the other components of the pseudo-orbit is a really cheap way to get a candidate, because we already have the initial condition.
But these gradient curves contained by perturbing all the observations, and they're running the gradient descent. Starting with those observations.
That's right. So and you can do that, yes, and that's more expensive. You can do that too. But every time you do that, you get the number of pseudo-orbit points as potential trajectories as well. So it's, yeah, does that make sense? So you can generate, it's easy to throw away bad candidates. And these you get virtually for free from the gradient descent.
Oh, I see. So you're doing one gradient descent, but you're collecting a number of late iterations.
No, the recipe varies depending on the ingredients, but the issue is you can't, yeah, that's right, you can go back and re-noise the observations and do the gradient descent again.
Yeah.
If the window is really long, you get results of comparable value. If the window is short, you fall farther away.
Yeah.
So but every time you do one, every time you have a pseudo-orbit within points, that actually defines in trajectories.
Mm-hmm.
And all of those are candidates.
Mm-hmm.
N is the number of...
N is the number of points, that's right. So N is the subspace corresponding
I think
to
so.
the
You
sequence space.
you can get one orbit from each one, so you...
That's right.
Mm-hmm.
So if in fact if your gradient descent actually converged to a true trajectory, then any one of those points would define all the others.
Mm-hmm.
The fact that the gradient descent hasn't quite converged to a trajectory, or maybe not at all, means that the n points, each one of them defines a trajectory, so you have n related trajectories.
Mm-hmm.
But if you're using a really long window, starting at the beginning, those guys are in Never Never Land.
Once you have those candidate trajectory, now we really use information of the observation noise model to draw ensemble members from those candidate trajectory. That's we measure the likelihood of each candidate trajectory and draw a random draw from them. Then eventually, since you have this ensemble trajectory, all you need is taking those points at t equal to 0 as ensemble, as nowcast ensembles. So we compare our method with one type of the ensemble common filter method, was developed by Anderson. Those are the equations. Those are the reference. So we'll first go to compare the method in a two-dimensional visualized version, so that you can see how the nowcast is working on a small dimensional systems. This was the attractor of the Akita, and we'll apply both methods on the Akita map. What we got is here. So the observation noise is 0.05, Gaussian RID, with standard deviation 0.05. For each method, we generate 512 ensembles for each nowcast. So here are 4 nowcast examples. I don't know if you can see those gray dots in the background. They are the attractor of the Akita map. And the cross in the middle, the red cross is the truth. The blue square is the observations. And the purple dots are the ensemble common filter ensemble members. And the green dots are generated by gradient descent.
No, so the blue square is the truth, and the red cross is the observation.
No, the red cross is the truth. The blue square is the observations.
At that time.
At that time.
There are lots of other observations which can't be seen now. They are outside the picture.
Yeah, but here are examples. So we try to nowcast the truth at that time. Right. So
with one observation.
No, with a lot of observation,
but
we
the
only plot the
observation at
result.
that time spot. So this is
the
an
slides at the
m-dimensional
t
slice
equal to 0.
through the m by n dimensional space.
Okay.
This is slides at the t equal to 0. Of course, to generate all these ensemble members, you have a lot of observation in the
In
past.
other places.
In the past.
Okay.
Right? But this is the truth at the t equal to 0. This is the observation at the t equal to 0. And these are the ensemble members we generated from both methods. We can see for the common filter method, these two examples looks they can kind of capture the truth. But compared with our method, they are not lying along the attractor. You see the background, the black attractor. They are not lying. The structure are very totally different. Well, for these two methods, they just completely mixed. Well, our method always captures choose and lying on the tractor.
So in this case, since the model is perfect, we would ideally be Bayesian, and then our prior would be zero, would be non-zero only in the area of those dots. Right? So because in this case we know from the dynamics that the points we're looking for that the prior is non-zero far from the attractor. But we have to be Bayesian and infinitely rich, not in the limit of large, but literally I think infinitely rich in order to implement that. So it really is the goal we're looking for, which is why we're happy the green dots are close to the attractor. So why are your dots all the same colors and my dots all different colors?
So I think Lenny showed some slides with the dots with different colors because he's weighting them according to the likelihood. Here, what I do is drawing the ensemble members from likelihood. I think statistically they are the same.
No, Lenny's is better.
You didn't know that. I do it because it's prettier.
Yes, the rule is never resample unless you absolutely have to, because of the introduction of an additional source of variation. So for computing means and variances, you use weights rather than a resampled, evenly weighted collection.
Okay.
Oh well.
Good to know.
Another thesis.
So to evaluate, so these are just 4 examples, but to test how robust the result is, we want to do some statistics and evaluate using some measure. The measure we use here, the score we use here, is the ignorance, which is the minus log p scores. The p is generated by the ensembles. We interpret the ensemble into a probability density function. For example, you can use like kernel dressing or kernel smoothing, Gaussian fit or whatever. Eventually, we generate those. We calculated the empirical ignorance for both methods. We can see that the ensemble member generated by green descent scores much higher than the ensemble common filter. Basically, you get like a lower ignorance for like more than 1 bit. So if the relative ignorance, if 1 divided by the other is -1, for example, if it's -1, that means one method is putting twice as more probability density on the truth.
Okay, so you've used log base 2.
Yes.
And it's minus, not divided. We've already taken the log. So these numbers are in bits.
Yes.
Yeah.
Okay. So now let's move on to the imperfect model scenario. So how can we deal with the realities? For the imperfect model scenarios, usually the model state space and system state space are different. If they're different, our goal is to say xt is the true state. Our goal is to find our goal is to estimate the true state, which is a projection of the system trajectory onto the model state space. And we assume our model is F, which is of course not the system model dynamics. And the observation is IID, and we assume the model error to be the one-step model error, just iterated by the model functions. So we have some toy models. We're using the Akita system as the for one example. We use the Akita system as the system, and using the truncated Akita map as the model. And one we use the large 96 and both fast and slow variables as the system, and only the slow variable as the model. So what's the difference when we use the gradient descent for the imperfect model scenarios? So let's think about this. The gradient descent usually give you if for numerical reasons it will give you a pseudo orbit. How that pseudo orbit will be a good estimate to the true trajectory, which project on the model trajectory. We know that the true trajectory project on the model trajectory will not be a trajectory of the model because the model basically is wrong. So we will expect the pseudo orbit if it's a very good estimate of the truth. we will expect that the implied noise, which is S minus the pseudo-orbit, which will be consistent. Think about the mu is the truth. You hope the delta is exactly the observational noise. So we hope that the pseudo-orbit will generate the corresponding implied noise will be consistent with the observational noise model. And also the omega I will be corresponding, the imperfection error will be corresponding to the model error. So if we get, our target is getting some good pseudo-orbits mu, which have consistent, which have implied noise consistent with observations, and with imperfection error consistent with model error. That's our hope. That's our target. And how's this implied noise and the imperfection error changed with gradient descent? We can see in the beginning the implied noise was 0 because we started with observations, and the imperfection error was very large. Then when we iterate forward, one goes smaller and one becomes larger. And eventually, the imperfection error goes 0 and the implied noise becomes very big. But we know that the model error shouldn't be 0. So what we do is we did a test. We did the statistics differently on the number of iterations of the gradient descent. Here the graph is all the axis is the number of iterations, and here the y-axis is the standard deviation of the implied noise, the standard deviation of the imperfection error, and the distance from the truth. And the black line is always corresponding to here will corresponding to the true noise level, the true standard deviation of the noise, and the true standard deviation of the model error. And here, of course, the closer to the truth, hopefully, is better. We can see that when we iterated the gradient descent, the implied noise goes to larger, becomes consistent with the observation noise, then it becomes overestimated. And the imperfection error becomes underestimated in the end. And the distance from the truth, you can see this minimum in the intermediate runs. So our conclusion is...
what's the difference between the left column and the right column?
Oh, the left column is for the Lorentz 96. The right column is for the Akita map, the model system.
So one's in 2D and one's in...
One's in 18D, 18 times 5 for the system.
But here, you made some assumption about that. I mean, you put in by hand noise and imperfection error.
Yes, we have the...
Are they all here of equal magnitude? Or?
Sorry?
Are they of equal magnitude here?
Which one has equal x to?
As each other.
You mean the Akita and the Lorentz 96?
No. I'm comparing implied noise and imperfection error.
Oh, so these two are very different things. One is the...
No, they're very different things, but what are they relative
magnitude? Okay. For Akita map, here the noise level is 0.01, and the imperfection error is 0.018. But for Akita map, we couldn't change the imperfection error at all. Here, for the Lorentz 96, I think the imperfection error is slightly smaller than the implied noise.
Within a factor of 2.
Within the factor of 2, yes.
So if they would be very different, then
yeah, they could be very different. We will see. We will see when they are different how we get the result in later. So our conclusion from the statistics, the gradient descent minimization with intermediate runs produce more consistent pseudo-orbit. We can generate the pseudo-orbit which has implied noise and the imperfection error consistent with the noise level and the model error. And we need some criteria to define when we stop the gradient descent. So we can use, for example, this graph, because imperfection error, the model error we don't know, this line we don't know, and the truth we don't know, we couldn't find the minimum. And the only thing we can know is the implied noise, is the noise level. So we can test the consistency between the implied noise and the noise model. And also we may minimize by other relevant utility function. For example, you are interested in the one-step forecast error being small. You can tune in the number of iterations based on that. Back to your question, just so it is very important to notice that the compound between the observation noise and the model error, how the magnitude between them. So when this is the real model error, and this is what we did, the part we had before. The noise level is 0.01, and these are generated by gradient descent with stopping criteria. We can see the imperfection error, the real imperfection error is 0.018. So these two look similar. So we have some good estimations. But when the noise is very small, so basically it will be noise-free case, you will estimate it, you can estimate model error pretty well. Right? If the noise-free, you can literally generate a model error. But when the noise level is large, you can see it's very difficult to see the structure here. So you kind of find it difficult to isolate the model error from the noise. So
do you have any ideas how you might do that?
Sorry?
Do you have any ideas how you might, in the case the noise level was larger?
In the case of noise level is large, I think this is still very difficult. We may try to find some spatial correlations, which the noise doesn't have, because noise is RID. You may not see the spatial correlation here very much, but you may be able to test it in statistically.
So when you say compare make sure that the consistency between the observational noise, do you have a cutoff for the likelihood, or do you?
So
do you see
it depends
that
on
the distribution looks good.
You can test it for down to the simple way is you test the standard deviation what they are different. You can look at, because if you assume that your observation noise is gassing, then you probably only look at the standard deviation. But if it's not, you may look at some standard test between two distributions.
So,
for example, like homograph.
So you make sure that the estimated state Z's are within the standard deviation of the observation. Is that a way of seeing it?
The implied noise are close to the noise model. The standard deviation of the implied noise are close to the standard deviation of the noise model.
And then you stop gradient.
Yes. Yeah, and also we see those. We see these bottoms. They are not so sharp. So you miss a little bit, or you underrun a little bit gradient descent. It doesn't vary. The result won't vary too much. What's the difference between our method with a weakly constrained 40 bar? The weakly constrained 40 bar often apply to realities. So last time Jonty helped me out to find. I found that there are many versions of weakly constrained 40 bar. So I don't want to really write a function. Then Jonty may say that might be a stupid way to do it with the weakly constrained 40 bar. So I summarize this. No matter how you write the weakly constrained 40 bar function is, you always need a model error assumptions, which is to feed to the weakly constrained 40 bar. Well, for our method is we have a gradient descent. We run the gradient descent and we generate the model error estimate. So we don't need the model error assumption at all. So this is a very different process. I think this is the major difference between them.
Well, I guess what you can say as the result, you get the model error estimates if they are larger than the noise error. If it's smaller, you can only say that it's smaller. You can't say how small it is.
Sorry?
You can only say
you
can only estimate model error if the model error is larger than the noise level.
No. Actually, the result I show you later is the model error is actually smaller than the observation.
But large enough. I mean, the magnitudes don't. It doesn't necessarily have to be larger, but But the point is right. If the model error is too small,
we can't estimate.
Then we can't estimate it. But if it's sufficiently small, it doesn't matter. So, but again, the advantage then is that we can go to longer windows. So we go to significantly longer windows, and then hopefully the model error starts to show up. But as long as it doesn't affect the dynamics, then we can't detect it.
You may not see the statistical difference with
so how do you do that? What information? How can you possibly get that information in general? What is the input that allows
the gradient descent to get? I think the input is you assuming your model is wrong. You know your model is imperfect, and you put your sequence of observation in, and then assuming, expect to get a pseudo-orbit, hopefully it's consistent with observations. If that pseudo-orbit is consistent with observations, you expect the imperfection error be a good estimate of model error.
Right, yeah. But I think the key, to some extent, the key thing is that that you're using knowledge of the noise model. I mean, you're reliant upon knowing something about the observational noise, and the advantage of that is you can measure that. You can actually do special experiments and hammer the observations to get information on the noise, to get information on the observational noise, where you can't do that with the modeler.
Yeah. Yeah. So it's like once you have the first one is like you have to put some priori of the modeler, while the others resulting give you the estimate without assuming the priori.
So you're not getting something for nothing, but you're getting something for something that you could buy if you wanted to.
Andres is saying you have to wrap up now.
Yes.
Sorry?
Andres is saying you have to wrap up now.
Oh, yeah, sure. So to form the ensemble, so we can apply the method by perturbing observations, run the gradient, or we can perturb the pseudo-orbits, run the gradient, or we can apply the gradient on other data simulation method, for example, particle filters, and then the cheap ensembles. So this is the result. Back to your question. This is actually for the Akita model system pairs with observation noise 0.05, while the model error is the standard deviation is only 0.018. It's smaller than the observation noise. Well, we can see still the truth is the red cross. The blue square is the observations. Here the background attractor doesn't make much sense now because we don't know the true system at all. So we do not expect our result lying on the attractor.
Why does the ensemble Kalman filter lie on the attractor in this case? Not
This
in
one
the
is.
case?
This one is not. This one is not.
Okay.
And this one is not. Sometimes it's just by chance it happens. And we can see these two cases, both methods works quite okay. It's sort of close. Ours seems much closer. And this one we covered, well, this misses. And this one, this misses, we covered. And this ensemble computer are using inflations. We can see for these examples, even you inflate even more, it wouldn't be covered the truth because it's just lying on the other manifold. The line while the truth is here, you inflate it won't help. Also, we use the ignorance to evaluate. We can see that our results, the green descent method is much more, it's outperformed the ensemble computer for about a bit. So, yeah, that's the end of my talk. Thanks. Any question?
One question. If you want to apply this in a real problem here, you need to, in order to apply this gradient descent, you need to store all the model states at the same time and perform gradient descent on all that data. That's a huge data set.
But we don't need to, so although the minimization is on the m times n dimensional space, but you don't need to store everything in the n times m matrix. All you need is you update each state by state, each component of the pseudo-orbit, point by point. So you still update them in the m-dimensional space. In
so
the m-dimensional
you need to have them on disk. You don't need to have them in memory. You only do manipulations of them pairwise. You only subtract states that are defined at the same time subslice. But you do have to have them on disk, right? But you don't have to have them in order.
No.
I mean,
Yeah, so next. Oh, yes. Yeah. So, do you have a laptop?
Laptop, yeah.
Yeah, good.
that resolution wasn't the same as mine. And last time we wouldn't know.
It also had the stuff at the top.
Yes.
screen on a Macintosh, so you have to print from my
Hold it up. It automatically throws it over for everyone to see.
It's a function F4 or something like that. I recognise the icon. So you want to go to mirroring. So I think we could go to settings. I'm making this up.
Only cool people can use Macintoshes. Even though we have people with Macintoshes. They just think they're cool.
We need
Yeah. I'll phone up my next week. No, not really. I'm not a paper simulation. No,
why not here?
I haven't really worked on it.
While we're waiting here, Anne asked you to return all your. Do we have enough key cards here? So, if you have
Okay.
thank you.
I already returned mine. Will you reuse the badges as well?
Badges? I don't think so.
I mean, you might still want to use them in the afternoon, right? If you want to come in.
So we're going to try.
We'll have to remember who we are. No,
You
you
want
mean
to come in the afternoon.
Oh, yeah, you might want to keep one.
No, I'm leaving on.
Okay.
Pretty
For
forward.
that.
When are you coming back? For passport?
Oh, you?
Yeah, the question is
I could leave it off.
there might be other
Working.
in the ones that.
Well, I mean, if you're, yeah, sure. Just don't forget to leave the message.
Okay. Always say it by mail if I forget.
So that is the curse of having a working laptop here. Everyone was using this.
Music on your desktop?
Huh?
Joo, voin olla puheenjohtaja, että molemmista löytyy ihan mukavasti tietoa internetissä.
Molemmista.
Molemmista puhujista ilmeisesti.
So people don't solve the problem. So we'd like to welcome Frank Wozniak. He got his PhD from Max Planck Institute in Hamburg, and he's working on dynamical systems and statistical and mathematical methods for climate and weather. And he has been for about 5 years at Exeter for the Center of Weather and Climate, which is in the math department. So thank you.
Thank you very much for the introduction. So my present talk today is on stochastic subgrid optimization. The outline of my talk is as follows. I will start with a short introduction, motivation into the topic. What is the work about? Then I will introduce a model system, a toy model I'm using to explore the methodology. It's a Lorentz 96 model. Might be well known, I will just briefly introduce it. Then I will introduce the methodology I'm using for subgrid modeling. It's an empirical methodology. The method is data-driven. I'm starting from a large data set of the system, to construct the subgrid model by forming empirical statistical relationships between unresolved and resolved scales. And then I will go through some results and discuss some results. What is the work about? It's in general about stochastic climate models, stochastic parameterization. We know the dynamics of weather and climate encompass a very wide range of scales, both spatially and temporally. So we, for example, if you consider the atmosphere, it starts from planetary scales, global scales, then it goes down to synoptic scale weather systems, mesoscale, microscale, the very smallest scales. And due to the nonlinear nature of the governing equations of motion, all these scales are coupled. So there is no clear truncation that you could build up a model for only some scales and then the other scales just drop out, but they are all coupled, so the small scales will have an impact on the large scales in a nonlinear manner, in a very complicated nonlinear manner. And that's a challenge. So how to account for unresolved scales? Because we are never able to resolve all the scales. Any computer model has some cutoff, some truncation level, neglected scales, and then we have to account for these neglected scales somehow. This is known as a closure problem. And one idea is to account for the unresolved scales by stochastic terms. To introduce stochastic terms into the equations for the large scales to drive somehow the large scales and to parameterize in this way the effect of the smaller scales, the unresolved smaller scales onto the resolved large scales. An important issue in this context is timescale separation. There has been a lot of theory for the limit of infinite timescale separation the area of theoretical physics. So if we can assume well separated large and small scales, then the problem gets easier. There's even a theory how to construct these closure models. Things get much more complicated if timescale separation is only weak or if there is no timescale separation. And that's unfortunately the case in weather and climate. Timescale separation is only very weak if at all present. For example, if you look at the atmosphere, there is this well-known graph of the energy spectrum of the atmosphere. There is no clear gap anywhere in the energy spectrum. It's just decaying quite smoothly. There is no clear gap in the spectrum. So it's a very weak timescale separation. And this makes the problem more challenging, much more ambitious in our context. So you cannot employ these theories of infinite timescale separation. There has been a body of previous work in this area. It maybe started in the 70s with a seminal paper of Klaus Hasselmann, where he first proposed to replace small scales by stochastic terms, so to add stochastic terms to a climate model. This was a very general proposition. He didn't go much further in detail. I think there were only 2 follow-up papers with Lemke from RV Bremerhaven, where they studied this a bit, but it was not elaborated very much. People came back to it later. In the 90s has been a lot of work on linear stochastic models, some by Cecile Penland, the Farrell group, Newman, and Zadeshbuk, who later did a lot in this area. This means linear stochastic model. It means we have a linear model for the interactions among the resolved scales. For example, the planetary scales in the atmosphere. We assume a stable constant matrix for this dynamics. Then we fit this matrix from data. That's a linear model. And then it's driven by Gaussian noise. In the simplest case, by Gaussian white noise. This accounts for the unresolved scales. This works surprisingly well, because the spectrum of the atmosphere is red. So it works to some extent, at least to capture linear properties, like autocorrelations or means and variances and fluxes in the atmosphere. However, it fails to capture, say, non-Gaussian features or regime behavior. This is genuinely nonlinear behavior and it can't be captured in this framework. Then people went further, recently to nonlinear approaches, nonlinear stochastic models. There's been a lot of work by the MIDA group. Andy MIDA developed this so-called MTV scheme. That's a rigorous stochastic closure scheme. And there has been a lot of work on this scheme. Minus Kauder, MIDA et al. It's a rigorous theory how to account for the neglected scales in a quadratical nonlinear system. It assumes infinite timescale separation, ideally, but fortunately it turned out that it's still of value even if timescale separation is weak. Even if, say, timescale separation is only 1 to 2, so it's only 1/2. So it's only weak separation, it's still working surprisingly well. Not clear why it's working that well, but it's still of value. Then there are other approaches, for example, due to Glenn Schatz, the so-called kinetic energy backscatter algorithm. There you inject kinetic energy at some smaller intermediate scales to capture the inverse cascade. So you re-inject energy, which is then transported upwards via the inverse cascade. This turns out to help to improve model performance. It was shown in the context of the ECMWF model. Then there are other approaches, Plant and Craig. I think this has to do with convection modeling, parameterizing convection. Then there is a special class of closure schemes, and these are the empirical or purely data-driven schemes. So this MIDA scheme is a semi-empirical. It uses information on the autocorrelation of the unreserved scales, but not really the full data set. Other schemes are more physically motivated. These are the purely data-driven schemes, purely empirical schemes, where you really start from a data set, and then without any physical reasoning, you just build up a closure model from statistics, empirically. There has been a paper by Wilkes, and recently by Crommelin van den Eyten. And my work is very much in line with these authors. So I'm talking about purely data-driven schemes. I'm studying my scheme in the context of the Lorentz 96 model. Just briefly, I think some of you know this very well, maybe some not. So that's Lorentz 96 system. It's a two-scale system. It has variables x and y. X variables are large-scale variables on a slower time scale. The y variables are on a smaller spatial scale and faster temporal scale. Each x variable is associated with a collection of fast y variables. Size of the system is a parameter. The variables are on a circle, so they mimic somehow meridional averages of the atmosphere. So it's a toy model of the atmosphere, and each x variable represents a certain segment in longitude. And that's averaged over latitude. Yeah, these are the equations. So we have advection among the large scales. Then we have a dissipation term. The advection and the dissipation term there. We have a forcing term. And then this B term is a subgrid term. That's the influence of the y variables onto the x variables. That's basically an average over the fast variables with some coupling constant. That's the subgrid term. Then the y variables themselves, they have advection among themselves, they have a damping, and they have a linear influence, a linear feedback of the x variables onto the y variables. The parameter epsilon is the timescale separation parameter. It makes the timescale separation explicit. So if epsilon is close to 0, it's infinite timescale separation. If it's close to 1, there's no timescale separation. Yeah, that's a model, cyclic boundary conditions. We take a parameter setting that was adopted by Crommelin, size of the system. We have moderate timescale separation, so epsilon is 1/2 here in our case. Yeah, and then some forcing and some coupling. So we have 18 reserved variables, and then almost 400 fast variables, which are to be replaced in the closure scheme. Yeah, that's a scatter plot of the subgrid term versus the x variable. So given x, this is the probability distribution of the subgrid term bk. So it's highly non-unique. Taking a fixed x value, we have a multitude of possible bk values. It's non-Gaussian. For some x, it's strongly non-Gaussian. It's quite scattered.
The line was the curve.
The solid curve is an estimate of the conditional mean. So that's a polynomial fit to this scatter plot. Fifth order polynomial. So that's maybe the best estimate of the conditional mean of bk conditional on x. The conditional mean accounts only for about half the variance of the scatter plot. This strongly suggests to add a stochastic term to capture the scatter. Then this is the anomaly plot. So if you subtract the solid line, if you subtract the conditional mean, we would build up a model which has always a conditional mean plus a stochastic term. Then this is the scatter, the remaining scatter to be modeled by the stochastic term. Now the methodology. I'm employing a so-called cluster-weighted subgrid model. This means the subgrid model is conditional on the state of the large-scale variable. We combine a clustering algorithm in the X space with a closure model. Then conditional on the cluster we are in X space, we use a different closure model. A collection of local closure models. And then we interpolate between them. We model the joint probability density. So that's a general outline of the method. We model the joint probability density of the subgrid term and a vector of clustering variable C. And then this probability density is modeled as a sum over clusters with a fixed number m of clusters. They have an overall weight W. Then they have an input density P. Given the cluster I, it has a certain density in C space, so in the clustering variable space. So this determines the domain of influence of a cluster, where it is located in X space. And then we have the predictive density given the cluster and given the state of the C variables. There is an output probability density on the subgrid term. The model predicts a probability density of the subgrid term, conditional on the model chosen and the state of C. And then you can introduce further conditioning. For this system, it turns out that the subgrid term has a high memory. So there's a high serial correlation subgrid term. This suggests to also use the previous value of the subgrid term to make the model dependent also on the previous subgrid value. Then the predictive probability density given a new state is a weighted sum of the individual predictive densities. And the weights Gi are state dependent, just given by Bayes' theorem. It's a state dependent weight of the individual cluster models. This framework is very flexible. You can choose these densities differently. An obvious choice would be Gaussian, both in the clustering space and in the subgrid space. Here we do a discrete probability density or discrete probability distribution in the X space. So we have a binning in the X space. Then we have a discrete distribution on these bins. And for the predictive density, we use a Markov chain. So we discretize the subgrid term bk into a finite number of discrete values. And then the system can jump between these states according to a transition matrix, which is state dependent. And this is, you might call it a cluster-weighted Markov chain. And the choice of the clustering variables, C, the variables you condition the chain on. Here choose the state x, so the discretized bin state x, and also the delta x, so the increment state. So delta x is the increment. It's a kind of derivative approximation. So if the trajectory goes upwards or downwards, we also condition our model on this. This is also discretized, so we have a binning in the delta x space as well. Yeah, that's a model. Yeah, there are some generic properties of cluster-weighted modeling. It has a transparent architecture with interpretable parameters. So you can put an insightful meaning on the parameters. Let's say it's different from a neural network, which is very much a black box. You cannot interpret parameters of a neural network. And this is quite transparent. So the Markov chain has a meaning. You can interpret the transition matrix of the Markov chain. You can interpret the clustering in X space. It has a certain meaning. Then parameter estimation in this framework is well established using the EM algorithm. So that's a very general class of algorithms, expectation algorithm, well known in the statistics community, and this can be put in the framework of EM. And then we do it by maximum likelihood. So we use EM algorithm to maximize the likelihood of the model. That's a very, very nice algorithm. It's provably convergent and has nice properties. And the whole framework is highly flexible, so you can vary these densities you put in or the conditioning variables. And the only hyperparameter in this method is the number of clusters. So the only parameter determined beforehand is the complexity of the model, so the number of local models you put in governs the overall model complexity. Yeah, there are the usual methods to determine this M. You could do a cross-validating, so take two data sets and cross-validate to determine the M. You can use just the model performance to just construct the model. Then you look how well is it when integrated. This determines the M. Or you could go even Bayesian, specify a prior on M and integrate it out. I think it's not really necessary. You can just do it by cross-validation or just by performance, by model statistics, output statistics. Yeah, now the results. So applying this framework to the Lorenz 96 model, what are the cluster states look like? We find a model with 3 cluster states, so M is equal to 3. What are these states? Well, that's a climatology in X and delta X. So that's a binning. So we have 8 bins. They are equally spaced, so they're not equally probable, but equally spaced in X space. And that's a probability distribution, so the invariant measure of the system. And that's a binning in delta X space. There we use only 2 bins, and they are just a positive and negative. So if the trajectory runs upwards or downwards, positive or negative increment. Then this is so the distribution is a bit skewed, so it's more often it's positive, it's running upwards. That's the climatology. Now our 3 cluster states compose this climatology, so they add up to the invariant measure. And that's the first state. It looks like this. So it's concentrated on low X values. First 3 bins basically. And it has no distinction or almost no distinction on delta X. First state has this weight, so it accounts for roughly 20% of the data. Then we get a second state on intermediate X values and strongly concentrated on positive delta X. So this model is taken in the middle of the interval and then the trajectory runs upwards in X. Accounts for about 40% of the data. Then we have a third state on intermediate and high X values and on negative delta X values. So that's when the trajectory comes back downwards. Third state, also about 40% of the data. That's the model weighting, so these state-dependent weights GI. So that's the local weight of the 3 models. The upper panel is when delta X is negative, and the lower panel is when delta x is positive. So for negative delta x, if x is small, it's almost only model 1. Then model for negative is model 3. So this dotted line is model 3, comes in for intermediate values. Model 2 is almost never used. And then if delta x is positive, again for very small x we have this first state, and then the second state comes in strongly. And it's a bit mixed also with the third state for high x values. So this corresponds to what we have seen and what the states look like. And now how is the model performing? So if we integrate the closure model forward in time and look at statistics of the x variable. This is the invariant measure of the system, so the PDF of xk. The solid line is a truth, so it's a full Lorentz 96 model. Then we have a dashed dotted, a dot dashed line. That's this one there. And this is a deterministic closure model. That's a closure model just taking the conditional mean of the subreturn. So it's just the solid line on this scatter plot. It's a polynomial fit. So that's a deterministic closure model.
So what's this graph?
This is a PDF of x when you integrate the closure model forward in time for a long time.
So this is how similar the invariant measures of the model are compared to the system for different closure models.
Yeah, yeah.
Thank you.
It's one particular. I mean, K has some
K doesn't matter because the system is invariant against translations. You can show this, so statistics is the same for all the x variables.
That is very similar. Are you interested? Are you interested that they're a little different, or are you interested that they look a lot alike?
They look a lot alike, but there are other variables where there's just a minute. Just let's explain what it is. Let's start with this. The dot dashed line is as a deterministic closure model, so just taking the conditional average. Then the next one is what is it? The dotted line. The next one is a dotted line here. This is a simple stochastic closure model taking an AR1 process. So that's the conditional mean, so the solid line, plus an AR1 process fitted to the remaining scatter. That's actually what Wilfs did in his paper of 2005. That's a simple model to compare against. That's a dotted line. Then the dashed line is my closure model with the 3 clusters, so the cluster-weighted Markov chain. So here we see that they all do quite well. The cluster-weighted model is a bit better, it's a bit more accurate. So they both have an error here. They underestimate this peak, and they are slightly worse here. And the cluster-weighted model is quite close to the truth. It's considerably better. But admittedly, for this variable, the simpler closure models already do it quite well. So they are all quite close. Now let's look at other variables. Let's look at the wave variance. The Lorentz model lives on a circle, so you can do a Fourier transform of the variables, and then study the variance of the Fourier components, like a spectrum in turbulence. Then you get this. Again, solid line is a truth, and again, dot dash is the deterministic closure, dotted line the simple stochastic closure, and the dashed line is the cluster-weighted closure. Here the difference is larger. Here there is really an improvement. The simple closure models have the peak spread out among wave numbers 3 and 4. And the cluster-weighted model gets the peak at wave number 3. There is really a significant improvement. Then look at temporal behavior, the autocorrelation of x. Again, the lines have the same meaning. The simple closure models have a considerable error. The autocorrelation decays too fast, and there's a phase shift. And the cluster-weighted model is quite good. It has just a small phase shift at large lengths. Then the cross-correlation among neighboring variables. Just take xk and xk plus 1, cross-correlation function. similar picture as with the outcorrelation. Decays too fast in the simple closure models. It's a more complex closure model gets it almost perfectly. Now prediction. How well do they predict? They are stochastic models, so ensemble prediction is a natural framework. So we form ensembles, and these are ensembles sampling only model uncertainty. So we do not perturb the initial condition, because there is no genuine initial condition uncertainty in this setting. We know the initial condition in X, so we do not perturb it. We just have a sampling, the ensemble just samples the model uncertainty. So the stochastic paths are different.
So, you know, Lawrence has this discussion of subtractable about whether or not the model, so I understand, so you have no observational error, but it's not quite the same thing as saying that there's no uncertainty in the initial condition. Right? Because, in fact, the model, even though they're both called X, they live in different state spaces. Then you actually look to see that changing, so our experience is, in that case, you often get a lot of information by looking at different initial conditions. Not that there's uncertainty in the true space, but there is uncertainty, there's effective uncertainty in the model space.
It may help.
Does that not help? Does that make a difference or not?
It may help nevertheless. I did this, it's in my paper. I can show you the results. It did not help very much here.
That's all I want.
So if you look at the overall skill, it's very similar. It doesn't help much. It helps a bit with the extremes. I come back to this when I show the extremes. Otherwise, there's not much difference. So that's the ensemble only with model uncertainty. And we have the solid lines are the cluster weighted closure, and they refer to different ensemble sizes. I think it's 5.
Solid lines.
And they are solid. I think, yes, they are solid. It's just a projection, as these are solid.
Okay.
They appear to be dotted, but they are not. They are solid. It's just the screen of the projection. They are solid lines. These 3 solid lines are the cluster weighted closure, and they refer to different ensemble sizes. I think it's 5, 10, and 50. Then the dashed lines are the AR1 closure, so the simple stochastic closure, and the dotted line is the deterministic closure. So there the ensemble is just a best guess, just a deterministic best guess forecast. So we see they all improve with ensemble size, as you expect. It's almost converged at ensemble size 50. It doesn't improve anymore. Then we see the deterministic model is worst, except for very small prediction horizon. There it's even slightly better than the AR1 closure. But for most of the legs, the AR1 closure improves on the deterministic closure, and then the cluster weighted closure considerably improves on the AR1 closure. Even with a small ensemble size 5, it's already better than 50 ensemble members with a simple closure. That's anomaly correlation, that's a root mean square error. And here they carry the same information, basically. It's the same picture.
And what's 15?
15 is the root mean square magnitude of the signal. Climatology. So as long as we are below the solid line, we have any skill. So we see, it's because the attractor is distorted. The deterministic closure model at large legs, it's even worse in climatology because it has the wrong variance. Then probabilistic forecasting, exploiting the full probabilistic information of the ensemble. This refers to 5 equally probable bins in X. So we have 5 classes of X, and then we have a probabilistic prediction on these 5 classes. And then we evaluate them using the range probability score and the ignorance score. Again, solid line is cluster weighted closure, dashed line AR1 closure, and deterministic closure, the single dotted line. That's the picture. So it's very similar to what you've got from the deterministic, so from the ensemble mean. The cluster weighted model is considerably better than the AR1 closure, already for small ensemble size. And this deterministic here is clearly off. It's clearly used as you expect. A single best guess forecast on these probabilistic bins, it does very badly because it's much too sharp. Yeah, same picture in the ignorance score. It's a bit different because the ignorance score strongly penalizes overconfident forecasts. So the deterministic model looks very, very bad in the ignorance score because it's consistently overconfident, much too sharp forecasts. And also the AR1 closure at small ensemble size. As you expect, they concentrate on some of the bins, which is not true. Then it gets strongly penalized with the ignorance score. Yeah, otherwise they carry roughly the same information here, rank probability score and ignorance score. So again, we have a considerable improvement with the cluster-weighted scheme. And that's prediction of extremes. We define an extreme event to be an event where xk exceeds as a 95% quantile of its climatology. It's in the upper 5, the base rate is 5%. And then we predict this event with the ensemble. We just use the raw ensemble. So we just make a probabilistic prediction. It's just given by the fraction of the ensemble lying in the extremal range without any post-processing. And that's a Roc curve. So we display the hit rate versus the false alarm rate. The solid line is a cluster-weighted closure scheme, and the dashed line is a simple stochastic closure scheme. We see again the cluster-weighted closure scheme improves on the simple closure scheme. So also for extremes, predicts better. Yeah, for extremes, it turns out to help a bit to perturb the initial condition. So it seems to carry strong information if you perturb the initial condition and then find that no ensemble member lies in the extremal range. That's a strong indication that there is a no event. And this improves the prediction in the upper part of the curve here, the upper part of the Roc curve. You get even further up if you perturb the initial condition as well. So there it helps. With the other settings, it doesn't help very much to perturb the initial condition. And then it turns out for the extremes, if you perturb the initial condition, it doesn't matter anymore very much which closure scheme you employ. So it helps a lot to perturb the initial condition, and then the differences between the closure schemes are quite minor. Because most information is carried in the cases where only very few ensemble members or no ensemble member is in the extremal range. And then it's strongly supported by perturbing the initial condition. And then the choice of the scheme has a minor.
Because Frank, that is obviously conditional upon your particular choice of scale separation parameter, isn't it?
Yeah, certainly.
So all of these are for epsilon equals 0.5.
Yeah, just for this case, yeah.
The whole system, right?
Yeah, but you could definitely imagine the balance between the information coming from the initial conditions and the information coming from the stochastic backscatter will be different depending on the separation of scale.
I think so, yeah. Yeah. Okay, that's the results here. Some remarks. What can we do with this scheme? Well, this scheme may be used in grid space in an atmospheric or oceanic model. So if you have a finite difference dispensation on the grid, you could use this closure scheme locally. Then you would condition the scheme on a certain grid point upon, say, the neighboring grid points. Or you can try to condition the system on meaningful clusters. For example, in the atmosphere we have the well-known teleconnection patterns, North Atlantic oscillation or Pacific North American pattern. So you would like to condition your closure model on the state of these patterns, for example. If the NAO is in a positive or negative phase, the closure may be different. It would be an even more interpretable closure then. In this Lorentz 96, these states themselves are just abstract states. They have no physical meaning. If you do this in an atmospheric model, you may hope to have a connection these well-known patterns. You might even start with them. You might define your conditioning variable C as, for example, the leading UFs spanning the NAO and the PNA.
Are you wrapping up?
Yeah, okay, yeah, okay. Yeah, I'm basically finished.
Yeah. That's a good wrapping up.
So I'm just wondering, you use the Laurent 96 system for the faster variable and combine with the slow variables. You usually can tuning the weights on the fast variables, basically your B terms, so that you can tuning that, make the model error large. Have you tried a different scaling? I mean, a different way. The one you showed seems the model error wasn't that large. I just wondering, using different the H you use the functions, the weights on the fast variables. Will that be impact on the model error a lot? I mean, it's very different. Show very different results for different models.
I'm not sure if I got your questions. Which way do you
So
want
you
to
have
say?
the
H's.
HX and HY.
So the H is the coupling between the
As a
fast and
coupling
slow.
in
So,
the-
so you can have the time scale with strong coupling, and you can have different time scales with weak coupling. So as H goes to 0, the model becomes perfect.
Yeah, okay. I didn't study this. I just took this coupling 1 and -1 standard setting.
yes.
So this is a considerable coupling. I have not looked at other variables of the coupling constant.
Thank you. So I think we have coffee, and then we start again at 11.
I have one question here. What is gradient sample?
I want to Frank, I'll come back.
Okay, yeah,
I'm sure you can.
So this is the, I guess,
That's very nice.
is it? Yeah.
Thank you.
Good.
Good night. You said you have a big
when you do
Could I
this,
take
it's
a
no longer observation, but I thought
It's
it's
not
analysis.
it's in the review stage.
Yes, but the FI changes.
I will send you once it's
Absolutely.
final
So you have
version,
these
once it's
related
finished.
Yes.
Okay.
Forecast.
Comments might be more useful earlier, but up to you.
So here is the function, the model.
Yes.
Okay, I
Very
will.
model here.
Yes.
So this is.
Yeah, okay, it's okay. It's for a special issue of philosophical
So
transactions.
then we
It's a
can
special issue related to this program of the
But here we
last
have
year.
Yeah.
We do a special issue. And I will contribute this there.
You make it.
Okay, I will send you. It's actually not really submitted. It's also written, but it's not submitted. I will say, okay.
When you minimize
I
it.
will send you as soon as submitted.
I mean, I'm just trying to scan it. So yeah.
Yeah,
I'm just
okay. I
curious.
would be grateful for your comments here.
So
So I will send you once I have
think
one established. Once I have first submitted.
That makes perfect sense. Good. Great. Thanks for your talk.
You?
You already also a letter today, right?
Yeah, I'm staying until tomorrow.
Yeah. Because maybe they I didn't quite follow everything. And so I would like to. So your noise is mostly this is additive, of course, right?
And then I end up.
Yeah, it's a closure, yeah. In this case, it's additive.
And
So
so the one thing that I could imagine could be
Oh,
make a qualitative change. If you have multiplicative noise on coefficients that would correspond to
we do need
diffusion
to
only.
Okay, so it's similar in that sense.
Diffusion coefficient, then you have fluctuations on that diffusion coefficient.
Because I thought
To
you
the extent such that
only need a
diffusion tendency at particular place become negative.
Yes,
very
when you
natural.
minimize,
Then you
Yeah.
would
when you minimize,
explicitly
you of course
have,
you
I
need
would
to
think,
add
Okay.
inverse
But
cascade
Cameron,
from those points, backscatter.
he also published a paper
Do you remember
about
that?
when you apply to a large dimensional system,
Yeah.
for example, like quadratic models,
Well, it's
you can use basically you can use
it's static, there's noise, so it's in some sense it's not
you can use a simple identity matrix instead of the actual.
I see. Okay, and why